So here is my first example. So I'm going to show you, you're going to have a lot of word problems. I'm going to show you how to pull the pieces from the problem, because that's one of the most important things, right? So you're going to have different hypothesis testing, which one is it in reference to, which one are you doing? So in a study of 1,228 randomly selected medical malpractice lawsuits, so let me write down notation. So this sounds like a sample size. It was found that 856 of them were dropped or dismissed. That sounds like a success, a piece of, right? So that is X, the number of successes. 856 were dropped or dismissed, okay? So I kind of want to remember what that represents. Were dropped or dismissed. Use a 0.01 significance level. So a 0.01 significance level. Significance level, if you remember, is alpha here. That is our significance level, which is always given to us. To test the claim, anytime I hear that, I'm going to set up my null and my alternative hypothesis. To test the claim that most medical malpractice lawsuits are dropped or dismissed. Now, I told you guys before, when you hear a claim about most rather than a mean or anything like that, it's always based on a population proportion. And when we say most, we're saying that the majority, meaning more than 50%. So the alternative hypothesis would be greater than 50% or 0.5. And the null hypothesis would be equal to 50% or 0.5. So let me go through it again and then see what I wrote as I pulled my notation from the problem. You want to convert the words into your statistical notation, and then you want to be able to go back and forth. In a study of 1,228 randomly selected medical malpractice lawsuits, sample size, it was found that this many successes, X, 856 were dropped or dismissed. So my success is dropped or dismissed. Use a 0.01 significance level, that's my alpha, to test the claim that most, more than 50%, that's a population proportion, greater than 50% or 0.5, medical malpractice lawsuits are dropped or dismissed. So if my alternative is greater than, my null is equal to. The null is always the equal to portion. So what kind of test do I have here? If it's greater than, it points to the right, so it would be a right-tailed test. Now, I'm going to gather all the information that you might be asked for here. We're going to gather the test statistic. We're going to gather the critical value. We're going to identify the p-value. We're going to identify, alpha. I'll put that over here too for you'll see. And then I believe that's it. Well, we'll do confidence intervals later. I'll just do the first two methods, and then I'll come and do confidence intervals, that method after. So we'll just find the test statistic, the critical value, and the p-value, which is kind of new stuff. And then we know alpha based on what they gave us. Now, when I'm running a test about a population proportion, I'm on a standard normal distribution curve. So my test statistic is a z-score, and my critical value is a z-score. Now let's start with the test statistic because that's very simple. This is the formula to find a test statistic for testing a claim about a proportion, which is what my situation is. And see, it's a z-score. So let me write that. Z is equal to p hat minus p over this thing. So I need to find p. I need to find p hat, which is sample proportion, and then q and then n. Well, I have n. I have p, right? P is the population proportion that I'm stating a claim about. And anytime I know P, I know Q. Q is the complement of P. Q is 1 minus P. So in this case, 1 minus 0.5 or 0.5 also. We have N. What else did I need? P hat. P hat is the sample proportion. From the sample, what is the proportion of cases that were dropped or dismissed? So that is the number of successes over N. So in this case, that would be my 856. Over 1228, which I'm going to convert into a decimal, and I'm going to probably take at least 4 digits to the right of the decimal place, 856 over 1228. So 856 divided by 1228, do that on the calculator, and we're going to get 0.6971. 0.697, approximately 0.6971. So let's calculate my test statistic down here using my formula. Z is equal to P hat, which I just determined was 0.6971 minus P, which is, basically the claimed value on the null, so 0.5, right, up here, divided by the square root of PQ over N. The square root of this big thing, P, which is 0.5, times Q, which is 0.5. This is a coincidence that they're the same here. It's not always like that. Over N, 1228. So let's say approximately. So z-scores we round to the nearest hundredth, 2 digits to the right of the decimal. Let's plug into my calculator real quick. So this is, going through the formula process. So here, let's do, I'm going to do the denominator first. 0.5 times 0.5, that value divided by 1228, and then I want the square root of that, square root of the following, and then I'm going to take the numerator, 0.6971 minus 0.5, and I want to divide that by the last result that I have on my calculator, so that's second ANS. 13.8. 13.8 is my test statistic for this. Now double check my work, make sure that I didn't make an error when I calculated that. Everybody, 13.81 if I round to the nearest 100. Okay, so we got the test statistic, right? The test statistic is 13.81. All right, so 1 down, 2 more to go, and then run my test. Critical value, let's do the critical value. The critical value is the value that separates the rejection region from, the rest of the curve. And because we're dealing with z-scores and population proportions, we're on an SND curve. Now, it's a right-tailed test, so the critical region, which is also known as the rejection region, is in the right tail. And we talked about this before. The probability of the rejection region, or alpha, right, is that area, in this case, to the right of what we call the critical value, which is going to be a z-score, right? So this is the visual, right? So this is the critical value, the value that is separating the rejection region / critical region, which has an area of alpha, from the rest of the curve on a standard normal distribution curve, because of the fact that I'm dealing with P's, population proportions. Now, if you remember how we determine or how we find a z-score, if I know the area to the right, second bars down to inverse norm, right? We said the area to the right was 0.01, so I'm going to do 1 minus 0.01. I'm on a standard normal distribution curve, so the mean is 0 and the standard deviation is 1. I'm always leaving this as left because not everybody has this option. And then I get 2.33, we'll say, 2.33 approximately, right? Rounded to the nearest 100. If I want to be really, really, careful about stuff, I can go even further, but typically z-scores, 2 digits is fine, 2.33. So my critical value is 2.33. So I have my critical value, I have my my test statistic, 2.33. Let's find my p-value, see if you remember how to do that. Also not very difficult. Same kind of thing from chapter 6. So a p-value is an area, right? And we said that the area to find the p-value is the area in the same tail as the rejection region. So the p-value is this area in the right tail. But instead of the critical value here, we have the test statistic. We have the test statistic, which is 13.81. So the p-value is the area corresponding to the test statistic that is in the same tail as the rejection region, but it's not the rejection region. When I talk about how we determine our conclusion, I'll show you, how technically you're kind of doing the same idea. They both do the same thing, but I'll show you the difference. So I want to determine an area corresponding to a known z-score, so second bars and normal CDF. My lower bound here is 13.81, and my upper bound is going to be a big, positive number. So I'll just put a 1 with a bunch of zeros. And then my mean is 0, my standard deviation is 1 because I'm on an SND curve. So this is the stuff we did in chapter 6. And I expect it to be very, very small. Look at this. 1.1557 times 10 to the negative 43. I'm going to just say that that is approximately 0, okay? Is that fair? Move the digit to the left, 43 values. Okay, so the p-value is approximately 0, which makes sense because if you look at your test statistic, it's really big. So this is not an accurate drawing because this should be all the way over here in the right tail with a tiny, tiny bit of area to the right. That's why the p-value is so small, because it's all the way over here, which, as you can see, the bulk of the area is within 3 standard deviations. As I go past that, I mean, this is 13.81 standard deviations away from the mean. This is a really big z-score, a big test statistic. Now, you might be asked for any one of these. Find the alternative, find the null hypothesis, find the type of test, find the test statistic, find the critical value, find the p-value. So we determined all of these pieces before, right? Now we're going to actually run the test. I didn't run the test yet. I want to know, what do I do? Do I reject the null or do I fail to reject the null? I have two options, right? So the first method that I said we can use is called the traditional method, right? The traditional method, I said, compares your test statistic to your critical value. If the test statistic is within the rejection region, then you reject the null, correct? I'll write that again. If the test statistic is within, which we'll talk about, rejection region, then we reject the null, right? That is the traditional method. Or if the test statistic is not within the rejection region, then we fail to reject the null. That's why we call it the rejection region. That's where we reject the null. So let's see, based on the traditional method, what our conclusion is. So where is the test statistic, in relation to the rejection region? So here's the rejection region, and the critical value separating this rejection region from the rest of the curve is 2.33. The test statistic is a z-score that is 13.81. So if I'm comparing that to this critical value and this rejection region, 13.81 is all the way in the right tail. The test statistic is all the way in this right tail. And all this area in the right tail is called the rejection region. So the test statistic is in the rejection region. It's to the right of the critical value because it's a right tail test, and that's the location of the rejection region. So the test statistic is in that region, and therefore we can say the test statistic is in the rejection region, and we reject the null. So our conclusion for this particular scenario is to reject the null hypothesis using the traditional method. So like I said, people prefer the traditional method because it's very visual. You can see where the test statistic is in relation to the rejection region. If it's in there, reject. If it's not, don't reject. Fail to reject. Okay? So that is one reason why some students prefer the traditional method, based on the nice visual of what your situation is. Now, second method was the p-value method. I'm going to do the confidence interval method after this, maybe in another example. Let me focus on these two first. The p-value method, we said if the p-value was less than or equal to alpha, we reject the null. If the p-value was greater than alpha, then we fail to reject the null. Now, this is basically you're comparing areas, right? You're comparing the p-value area to the alpha area. So in this case, my p-value was approximately 0, and my alpha was 0.01. So you can clearly see that 0, which is the p-value, is less than alpha, which was 0.01. And because the p-value is less than alpha, then we come to the conclusion to reject the null. I claim that these two methods are basically doing the same thing, and the reason that I claim that is because I said if the test statistic is in the rejection region, you reject, right? So the test statistic is over here. Well, the p-value is that area corresponding to the test statistic. So the p-value, if I put the p-value on the same curve along with the test statistic and the critical value and the rejection region. The p-value is over here, right? This p-value is this area to the right of the test statistic. Well, if the p-value is an area that is smaller than alpha, which is all of this, then wouldn't that imply the same thing as the test statistic being in the rejection region, being to the right? This test statistic is to the right of this critical value. So therefore, the area to the right of it would be less than this whole area here, which is alpha. So stating that the p-value is smaller than alpha is basically the same thing as saying that the test statistic is within the rejection region, or in this case, to the right of the critical value because of a right-tailed test. Before I finish, right? Once you state your conclusion, which is to reject the null, right? There are two ways you can go. I said to you, if you're rejecting a null, throwing it out, rejection is like to throw it away, then you are supporting the alternative. If I am rejecting this, imagine like I'm rejecting it, therefore I'm supporting this. So let me write that. If I reject the null, there is sufficient evidence to support the alternative, which is the claim that, well, let's go back to the alternative. What does it say? P is greater than 0.5. That most medical malpractice lawsuits are dropped or dismissed. Most medical malpractice lawsuits are dropped or dismissed. There is sufficient evidence to support the claim that most medical malpractice lawsuits are dropped or dismissed based on the fact that we are rejecting the null from all my different tests. And when I reject this, I support this, which states that P, the population proportion, which represents the proportion from the population that out of medical malpractice lawsuits that are dropped or dismissed, saying that it's more than 50%, which would imply most. Typically, like with confidence intervals, all the terminology, all the interpretation is very consistent, very repetitive, and basically comes from the question. I'm basically copying now on the question. As long as I say that if I reject this, then I support this. There's sufficient evidence to support this. Otherwise, if I were not rejecting this, failing to reject this, then I could not. There's insufficient evidence to support this. And then you want to make sure that your terms, your notation, follow what you're saying verbally. So you have to understand what the notation and the variables represent corresponding to your situation, because you're going to go back and forth between words and mathematical terms.